The last time we were all together in this room 2 weeks ago, it got kind of hot in here. And when I came in here, it still felt a little stuffy, so I went ahead and opened the windows. I think that's okay. Temperature management seems to be a difficult thing. Okay, so yeah, when I made the schedule before the semester started, for some reason I budgeted 2 class periods to cover the section on the solving systems of nonlinear equations, but I covered all that one day. So I didn't want to have to like change the schedule, so like I think it's a good break a little bit. But now we're resuming the schedule, and the rest of the semester it's all about numerical methods for solving ordinary differential equations. Initial value problems first, chapter 12, and then we'll do some of chapter 13, the boundary value problems. But first, a few words about the final. Part of the syllabus, but there are 2 options. So there's a oral final exam, and that is comprehensive. Now, when I first wrote this, we were still in the middle of a pandemic, but I can do it virtually or to be in the office, like, so you can write on the board. And the other option is there's a coding project. Okay. That is posted in Canvas already. Let me make sure it's accessible. Might not have published it yet. Oh, okay. It's not until now. So on the assignments page in Canvas, you can see that. So this is the coding option that so it's described here, and there's some starter code for that. Now, the coding option is the opposite of comprehensive. It only deals with the last portion of the course, chapter 13, on the boundary value problems. So when we get to that section, those sections, you can decide which option you want to take. And I want to have all work submitted, because I know I have not been enforcing deadlines, and so not a whole lot has been turned in by some people. But at some point, we all just run out of semester. Everything has to be in. So Thursday, May 9th, which is Thursday, it's the last day of finals. That's when I want to have everything in. Also, whichever option you choose for the final, that's been administered by them too. There are a total of 9. Okay, 8 quizzes. Okay, there are 9 homeworks, but the lowest 2 get dropped. Ease my grading burden. Okay, so something for you to put in the back of your mind as to how you want the end of the semester to go. And I'll have more to say about the oral portion when we get closer. But because it's oral, we would not be doing MATLAB type things. About concepts. So kind of like the quiz questions. Put on the spot. So now, we're ready to dive into ODEs. So the kind of problem we're going to consider in this chapter is numerically solving a general first order initial value problem. So I'm just going to have this form. So y prime is a function of the time t and the solution y. And then we have so initial time t naught and final time capital T. Usually the initial time is 0. And then we have some initial condition that specifies the solution at the initial time. we make an assumption about F. F satisfies a Lipschitz condition. We've seen the Lipschitz condition before from fixed point iteration. Basically means that notice that in this Lipschitz condition, F is a function of two variables, but we have the same value plugged in for t, but we have different values plugged in for y. So it's not just satisfying Lipschitz condition, we say it satisfies a Lipschitz condition in y. So the difference in F values at different y values is bounded by a Lipschitz constant times difference in y values. So another way of putting it is that the partial derivative of F with respect to y is bounded. Absolute value by L. We use the Lipschitz condition because we don't want to have to assume that F is differentiable with respect to y. Unlike fixed point iteration, there's no expectation that the Lipschitz constant has to be less than 1. It just has to be a Lipschitz constant. So we're not requiring that to be a contraction. Okay. Now, the reason we make this assumption on F is that it guarantees that the problem is well posed, that there is a solution exists, a solution is unique, and also the solution depends continuously on the data, meaning that a small change in the problem data, like the initial value or function f, is not going to cause a large change in the solution. In some classes, introductory classes on solving ODEs, like Math 285, if the instructor wants to pursue it, which might not, they might go ahead with a proof, what's called the existence uniqueness theorem, that if F satisfies this Lipschitz condition, that there is a unique solution. When I teach Math 285, I do like to do that proof, even though my students find it painful, but it can be enlightening. But I want to mention it here anyway, because I'm not going to do the proof here, but it uses fixed point iteration, something that we've just seen. It is applied to this expression for the exact solution. So the exact solution of our initial value problem can be written, actually, there's a slight mistake here. The lower limit should be not 0, but or general initial time t naught. So in proving this existence uniqueness theorem, it involves applying fixed point iteration, where this right-hand side here is the function g. So you take your solution y of t, you substitute it in here, and you do one. They're called, in this context, they're called the Picard iterates. So no, not that Picard. And what you show is that this g, under the right assumptions, is a contraction mapping. So fixed point iteration is guaranteed to converge. So, and we use fixed point iteration to solve, to find a root of a function f of x, but fixed point iteration is used in the wide variety context often to prove that a difficult equation like this one actually has a solution. And also that the solution is but here what we're interested in solving this equation approximately, because in class like Math 285, you learn how to solve certain first order ODEs. Like for instance, separable equations, exact equations, using integrating factors, things like that. But those techniques are only helpful for rather narrow subcategory of first order ODEs. So this is once again the contrast between numerical methods and analytical methods. We're going to look at methods that produce an approximate solution, but they can be applied to any ODE in this form. Whereas what you know so far from your ODE class is you know how to solve certain ODEs exactly, but your repertoire is very limited. And the thing is, all those things you would have learned about first order ODEs from a class like that, you don't need to know any of those here. We're not going to use those things. That's actually why I had map 285 as a prerequisite for 461. Okay, so how do we go about solving an ODE numerically? What we do is we perform time stepping, solve this initial value problem. So the idea is we're not going to compute a function y of t like you would in when using analytical methods. Instead, we're going to compute the values of a solution at select times. So we're given the value of a solution at t naught. That's our initial condition. So we're just going to compute the solution at times t1, t2, and so on. And all of these times, we're going to assume equally spaced. So each time is equal to the initial time plus the index I times h. So h is going to be very important here. H is the time step. So for simplicity, we're going to assume that we're taking uniform steps of uniform length in time. Well, all the time values are equally spaced. That isn't necessarily true in practice. Now, in this class, we're going to learn about different ways of classifying numerical methods. One classification is one-step versus multi-step. So the idea is a one-step method is if we know a solution like at time tn, that's yn. Look at the notation here. Y sub n, the subscript, that indicates the approximate solution. Y of a time value, that refers to the exact solution. So yn is an approximation of the exact solution y at time tn. So if we have an approximate solution at time tn, and we want a solution at the next time, yn plus 1, because we're marching forward through time. The one-step method uses information only on this interval. So from the time we're at to the time we're trying to get to. Hold on. Those trauma classes. Whereas multi-step methods use information earlier in time. And we'll see those later, like next week. Now, today we're going to look at the simplest one-step method. So one-step methods generally use Taylor expansion. So what I'm doing here is I'm taking a Taylor expansion of y around the center Tn. And I want to use Taylor expansion to express the solution at the next time, Tn plus 1. So if I carry out Taylor expansion, but only as far as the second derivative term. So y of tn plus 1 would be y of tn plus h times y prime, but y prime is equal to f, so we fill that in here. And then this last term is a remainder, Taylor remainder. So 1/2 h squared, second derivative at an unknown point between our center and our evaluation point. So we're going to use this as a foundation for the simplest possible numerical method. So what we do is we drop the Taylor remainder. And now we have, well, this is what's left here. So our approximate solution at time n plus 1 is equal to approximate solution at time n plus h times the derivative, which is taken from f. And we just keep carrying this out to advance from one time to the next. And this is called Euler's method. Euler, not Euler. So Can't get any simpler than this. So what I'd like to do here is actually prove that this method actually works. That if we, as a time step h goes to 0, presumably we should be getting more accuracy. So we can also show that as h goes to 0, that the computed solution produced by Euler's method actually converges to the exact solution of yt. So I need to define what it means to have convergence. So right here, inside the absolute value, we have the error, so the exact solution at time tn minus the approximate solution at time tn. And we'll just take absolute value. But then we examine this over all time steps, because we're time stepping from time t naught to time capital T. So the number of time steps we're going to take, n, is at most this quantity, t capital T minus t naught divided by h. So what I'm highlighting here indicates the maximum error over all time steps that were taken for the given value of h. So here we have a maximum error for a fixed but still positive h. So we want that maximum error to go to 0 as h goes to 0. So then we take the limit. So if this holds, then the exact solution, the computed solution really does approach the exact solution at every time value between t naught and capital T. And so then we say the method, this time stepping method converges. Questions about the notion of convergence? Okay, so I'm going to prove that Euler's method converges. So here is Euler's method repeated right here. And then down here we have the Taylor expansion that I gave earlier. So here we have computed solution, exact solution. As before, we assume that function f, that represents a time derivative, satisfies the Lipschitz condition in the y variable. So then what I can do is I can subtract these equations. So on the left side, I have the error. So this minus this is the error at time n tn plus 1. So you have that on the left side. On the right side, so we subtract this minus this. Oh, actually, sorry, other way around. This minus this, that's how I define the error. So approximate minus exact. So here we have the error, this minus this, at time tn. And then I subtract these also. And then we have the Taylor remainder. So we have this relationship between the new error and the previous error, from one time to the next. Now, for convenience, we assume that y is twice continuously differentiable, meaning this second derivative is continuous on this interval. Because then we can use the fact that a continuous function on a compact set has a minimum and maximum. So we're going to so therefore we have at the absolute value y double prime is bounded above by this constant m, capital M. Yeah.
Does it go back to the axiom of this, like bounded sets have?
So whatever is used to driven by compact sets, all that, all real analysis things. Okay. Okay. Now, so if I take the absolute value of both sides, use a triangle inequality on the right side. Well, here I have a difference in f values, where the t value involved is the same. So for this difference of f values, I apply the Lipschitz conversion. And what are the y values in question here? Computed solution minus the exact solution. But that's En. So this difference in f values here is bounded above by the Lipschitz constant times the difference in y values. But that difference in y values in this case, this minus this, is En. So now we have a simple relationship between the error at the new time and the error at the previous time. And then bounding this, using the bound second derivative, gives us this. But now we see that the error can possibly grow over time. But we want to make sure that that growth does not get out of hand as h goes to 0. Because as h goes to 0, presumably we're getting more accuracy, but we're also taking more time steps. So there's a trade-off there. But yeah, so efficiency becomes an issue. And is the greater accuracy worth it? Now, what I have here, you can think of as a recurrence relation, because I have the relationship between the new error and the previous error. So what I can do is I can apply this relationship repeatedly. So, En plus 1 is less or equal to 1 plus HL times En. But En, I've expanded in here in terms of En minus 1. And then I also expand En minus 1 in terms of En minus 2. So I get this nesting happening when I apply this relationship multiple times. Now, if I keep this, so now if I expand all this and group everything together, what I get is, notice I have 1 plus HL times 1 plus HL times 1 plus HL. So I have 1 plus HL cubed times the earlier error. And then I have all these terms, h squared m over 2, but they're multiplied by various powers of 1 plus HL, so those will be gathered here. So, so notice here we have consecutive errors at consecutive times multiplied by 1 plus HL. Here, En minus 2, that's from 3 time steps before this one. So we have 1 plus HL cubed. So extrapolating from the pattern that you see here, this is what I get. That I can express the error at time n in terms of the initial error, and we're multiplying by 1 plus HL to the n. And then all these terms gathered here, we have this summation. Now we have h squared m over 2 as a common factor. Then we're adding up all the powers of 1 plus HL from the 0th power up to n minus first power. But this sum is it's a geometric series, or truncated geometric series. This is something I would cover in Cal 3. And in Cal 3, I presented there's a formula for of a partial sum in closed form. That what I get, okay, here's a formula right here, the general formula. If I'm adding up these powers of some number r, or in this case r is 1 plus HL, then this is the formula for a partial sum. So then, what I end up getting from this formula is this divided by HL. Now, here I've simplified all of that. So notice here we had h squared, but now we only have h because there was a factor of HL that caused it to get this. Also, we have this factor of L appearing in the denominator. Now, we're also assuming that the initial condition is exact. In other words, E0 is 0. So there's no error at the beginning. Now, that's not always true with factors, you might have rounding error, but here we'll assume it's exact. So this term actually goes away. So all that's left is the error at time n is now bounded by this. So now we have an explicit bound because Before we had the bounding the error in terms of a previous error, but now we don't have that anymore. We just have this expression, but we want to see what happens with this expression as h goes to 0. Okay, but also as h goes to 0, and it's also going to infinity. So questions about getting to this point? Now, make things simpler. This expression here, 1 plus HL, this HL times L is positive. I could say that this is less than e to the HL. So I replace, so this right here is actually the first two terms of the Taylor expansion of e to the HL. So I fill in e to the HL down here, and we also have the factor of n in the exponent. But n times h is difference between time tn and time t naught. But that is at most the length of the entire interval in time. So now I have a bound for the error at time tn that doesn't involve n at all. I want to know what happens if this h goes to 0. So here we have a very simple dependence on h. So everything here, everything else, everything that I've highlighted right here, that's a constant. It can be a pretty large constant, but it's still a constant, totally independent of n and h. So then it's easy to see that as h goes to 0, all of this bound goes to 0. So this completes the proof that Euler's method converges. Also, we say Euler's method is first order accurate because here this bound on the, what's called the global error is proportional to h. So using the term I introduced last semester, the error is big O of h. Now, that's actually not great. We would like for the error to be bounded by a power of h, greater than 1, order h squared or order h4. We will learn about methods that have that property. But here we have such a simple method, Euler's method, we can't really expect much from it. But at least we see that it works. So questions about how this convergence proof played out? Okay, now, some comments about what I just did. Do some math stuff to show you. Okay, this what I've shown is oversimplification because there's no round off error included. Now, actually, I can show you something about that. Okay. All right, so this is what was arrived at before. Now, if I wanted to account for round-off error, I would have something like this. So my product solution values are called yn tilde and yn plus 1 tilde. We assume that Euler's method introduces this some rounding error. So delta n plus 1 is attempt to quantify that rounding error. And we're going to assume here that this quantity is a big O of U. U is a machine precision or unit round off. That's discussed in chapter 2. So we're assuming that some small error, rounding error, is included here. So then I would repeat the convergence analysis I just carried out with this extra term in here. And here's what happens. So we have this error bound. Now, a portion of this is what I already had before. But now we have this new term, delta over H. And then I have this term here also that features around the rounding error delta. So delta is a bound in the rounding error. But watch what happens. As H goes to 0, okay, this part goes to 0, that's what I had before. But then this part goes to infinity. So what happens is the round off error accumulates over all your time steps and eventually wrecks everything. Now, last semester when I covered numerical differentiation of Twice Silver with this, it was like a forward difference, like f of x naught plus h minus f of x naught over h. And as h gets smaller and smaller, you see it computes a derivative more and more accurately to a point. At some point, once h gets small enough, the error increases because rounding error takes over. That keeps increasing as h goes to 0. So we don't want to use h too small. What you could do is try to solve for h so that this factor here is as small as possible. So there is an optimal h that you can try to figure out. That would depend on the bound of the second derivative, for instance. So you have to be careful about that. That once you throw rounding error into the picture, it can wreck. Well, not everything, but it's so you have to be careful. Now, I have an example for a very simple ODE, y prime equals minus y, so the exact solution is e to the minus 2. And here we have this bound on the error. And so let's suppose that we want the error at our final time, in this case capital T equals 10, to be less than 0.001. So what I could do is I could require this quantity here to be less than 0.001 when I plug in Tn equal to capital T. So then I work out what all this is, figure out what capital M is, figure out what capital L is, and I end up with this expression here that the error is less than or equal to this large number of over 1,000 times h. Now, if I want this to be less than 0.001, and I solve for h, I get a pretty small recommended value, so 9 times 10 to the minus 8. But this error bound is not a sharp bound. So, I mean, we can't say that this error is less than or equal to this expression, but it's not exactly in the ballpark. This can easily be much greater than the error we're trying to bound. So in other words, the h that this error bound suggests is going to be way too conservative. So I want the error to be less than 10 to the minus 3. If I actually do use this outrageously small time step on the order of 10 to the minus 8, then I get error 10 to the minus 11. That's one thing to keep in mind. Like often when you're analyzing divergence, you're trying to find a bound for your error. But if that bound is not a sharp bound, if you're taking liberties with what's less than or equal to what, and you don't care about if you don't care what your expressions are possibly much greater than what you're bounding, then the error bounding you get might suggest that h-bet is smaller than necessary. To give you an idea what I mean by a not sharp bound, like I did that here, I have this expression 1 plus HL, and I say, oh, well, that's less than e to the LH. Well, that's true, it is. But this is not a sharp bounding channel. As an example, let's suppose I have, well, if I plug in x equal 1, then I have 2 on the left side, and I have 2.718 on the right side. Okay, even then that's not great, but not outrageous. But e to the x will grow so much faster than 1 plus x that, like, if I plug in x equal 2, I'll have 3 on the left side, then I'll have e squared, which is going to be 8 or so. So it's just going to get worse and worse. So that's something to keep in mind. And there's other things here that also are indicative of not sharp bound. Okay. Now, there's one section that in this chapter, unfortunately, I won't be covering it. It's section 12.5, which is on adaptive methods. So what that adaptive methods do is they estimate the error in a more sophisticated way than what I just showed you at every time step, and uses that error estimate to determine should it change the time step. Does it need to make it smaller to ensure more accuracy, or maybe you can get away with something larger, therefore still get enough accuracy with greater efficiency. So practical implementations of time stepping methods, like in MATLAB, use adaptive time stepping to set an appropriate effective H, balancing those concerns of accuracy and efficiency. So in fact, speaking of solving ODEs, I'll show you how that's done. So how to solve ODE in MATLAB. Let's do the simple examples here. On the simple ODE, y prime equals minus y. Additional condition y is 0 equals 1. On the interval from 0 to 10. So 10 is my final time. So what I do is I define a function f by time derivative. It's a function of t and y. But in this case, so for general first order ODE, we have y prime equals f of ty, but that's just going to be minus y. And then my initial value, y naught, 1. And then my time span is a vector consisting of my initial time, 0, and my final time, 10. I could put more times in here if I want, but for now I'll just put in 2. And now I'm ready to actually solve the ODE. So MATLAB has several functions that are ODE solvers. Here's one of them, ODE 2.3. So first parameter I pass is a function f, and then I have my time span, and then my initial value. And there we have it. Let's compute a solution. But let's take a look at what it computed. So the output, we have a t, which is a vector of t values between 0 and 10. Now, they're pretty irregular times that I use. So what I'm going to do is, I want to show you the time steps that it took between times. And for that, I can use diff of t. So all diff does when you apply it to a vector is just computes like this minus this, and then this minus this. So some differences of consecutive elements. So by taking diff of this vector of time values, I'll get to see the time step length. And notice in this area, it's using a fairly uniform time step, but then it starts to increase toward the end. Here, take a smaller time step at first, but then it gets a little bit larger, settling on a fairly uniform value. So this is an example of what MATLAB ODE solvers do, the example of adaptive time stepping, where it's adjusting the time step to get the balance, accuracy, and efficiency. Now, this ODE solver, ODE23, uses a time stepping method that's called the Bogacki-Champine method. Lawrence Champine is one of the lead author on a paper called the MATLAB ODE suite that describes all the ODE solvers. The Bogacki-Champine method is that method that uses two what are called Runge-Kutta methods. Runge-Kutta methods I will be covering later. And the 2-3 indications methods that it uses are of second and third order accuracy. So the error is proportional to h squared or h cubed instead of just h, like Euler's method. So this is one of several ODE solvers that MATLAB has. Now, how accurate is this? The exact solution is yt equals the exponential of minus t. So I'm going to extract our figure windows. Then I'll do plot the exact solution in blue. Okay. And then I'll label my axes. And then I'm going to plot my computed solution. So y is the vector of my solution values. And I'm going to plot them using red circles so that we can compare. And we see, at least as far as this plot is concerned, it's pretty much dead on. And yes, there is error, but we can't even really distinguish the two solutions on a plot. But once two values are within like 10 to the minus 3 of each other, it's pretty hard to distinguish on a plot. Okay, I'll throw in a legend here. Exact and computed. You can see the legend there. See their solutions which. But how accurate is this really? So what I can do is use the norm function. So here I'm taking the norm of a vector, so I subtract the solution values minus the exact solution values, and I take the norm, which by default, norm is going to, for the vector, it's going to take, it's the 2 norm. Remember I talked about norms when I covered iterative methods. So it's a square root of some squares of all components. And then I'm going to divide that, I want relative error, by the norm of the exact solution. And what we get is, yeah, the error is pretty small. So on the order of 10 to the minus 4. So that explains why these solutions are quite close here on this point. So it did a good job. But this is also a very simple ODE. Better do this. Now, there are options I could set, like if I wanted more accuracy, I could set a tolerance in the ODE solver to force it to get more, to take smaller time steps to get more accuracy that way. Now, one thing to keep in mind is if you are solving PDEs, so you would discretize a PDE in a system of ODEs, and that you can solve in MATLAB. PDEs. What I suggest in that case, using what's called a stiff solver, such as ODE 15S, so the S is for stiff. Now, the concept of stiffness is one that I will cover later in this chapter. So a lot of problems of interest are the systems of ODEs that are stiff, and those difficulties for kind of time study methods that I'm going to show you. So for systems like that, if I use a solver like the one I just did, like ODE 2.3, it would actually not go very well. It would be quite inefficient. Something like ODE 1.5 has to do much better. So to keep in mind that not all of these solvers are created equal. But the reason why MATLAB has such a large collection of them, but certain ones are that are suited to certain problems. Okay. Well, come to the end. So are there any questions about anything? All right. Well, I guess we can square.